Hey everyone, we're going to look at number 20 in section 5.4. This instructions are to evaluate using the fundamental theorem of calculus part 1. And here is the definite integral we're evaluating. I just want to recall when we were finding the antiderivative e to the 3x, that's not going to be e to the 3x. Remember, the integral in general of e to the kx dx is 1 over k e to the kx. And the reason is if you take the derivative e to the kx, you've got a chain rule going on, right? And the derivative will be e to the kx times k, right? Or k e to the kx. So when I multiply by 1 over k, I end up with the derivative of this function here being e to the kx. So this is the antiderivative of e to the kx. Okay, so with that, I just want to find the antiderivative of the function here that we're integrating, and then I'll reevaluate this definite integral. So let's just do the indefinite integral here. So the antiderivative of 13 times x, we'll pull the 13 out. The antiderivative of x, right, is x squared over 2, or 1/2 x squared. Here I'll pull out the 27, and the antiderivative of e to the 3x, as we said up here, k is 3, I get 1/3 e to the 3x. Cleaning this up, I get 13 halves x squared. 27 times 1/3, or 27 divided by 3 is 9. So I got negative 9 e to the 3x. So there's my general antiderivative. So now I can use the fundamental theorem of calculus part 1 to evaluate this definite integral. The antiderivative of this we just found to be 13 halves x squared minus 9 e to the 3x. Right? And then we're going to evaluate this at the upper limit of 0, lower limit of -2. If I plug in 0 first, this will be 0, but this, be careful, e to the 3 times 0 is e to the 0 is 1. I get minus 9. So 0 minus 9, I'll get -9 when I plug in 0. So this is the evaluation at 0. This is the evaluation at -2. Squaring -2 gives me 4. 2 goes into 4 twice. 2 times 13 is 26. And here I plug in -2, I get minus 9 e to the 3 times -2 is -6 power. So clean this up. I got a negative times a negative is a positive 9 e to the -6, and I have -9 minus 26 is -35. So there's the exact value of this definite integral.